Hello! In previous material, we learned how to take a system of linear equations and convert it into an augmented matrix. The augmented matrix consisted of a coefficient part and the augmented part on the right-hand side. Inside this section, we're going to learn how to operate with the coefficient part of the matrix as its own type of mathematical object, much in the same way that we learned how to operate with vectors as their own types of mathematical objects. So recall that a matrix is a set of numbers that's arranged in a particular way. We have a stack of numbers in each row going left and right, and we have a stack of numbers going up and down in each column. So again, columns, they're what's indicated by that red rectangle. They go up and down. We would indicate that that column highlighted in red there is the first column of the matrix. The second column of the matrix would be this one, and then the third column of the matrix would be that one, and so on. We'd keep marching to the right as we move up in column index. The rows go left and right. So that first row is the one that's highlighted in blue. The second row would be the one that's directly below it. So I'll highlight that. So that would be row 2. And then row 3 would be below that. It's not shown. The numbers are not indicated for it, but it would be the next row beneath row 2. So a selection of rows and columns for this matrix have been indicated. Now the reason why this matrix looks weird with the dots on it is because it indicates a matrix of arbitrary size. The dot just means that there's potentially lots of columns and rows that are in between that are not showing, because you can't show necessarily, let's say, a 100 by 100 matrix all in one page. You gotta be a little careful with the next part. Remember the I and j from vectors? You have a unit vector in the I direction, which is the x direction, unit vector in j direction, which is the y direction. We're not going to use I and j in the same way here. We're using them as a type of counter, as an index counter. The notation little aij refers to the matrix element, so the number that's at row number I and column number j. This isn't the greatest notation in the world because it's extremely ambiguous if either the row number or the column number exceeds 9 when you get into double digit or triple digit numbers. Because of that, there's an alternative notation that's much more precise and it's much less ambiguous, and that's the ij in bracket notation that's here. It still indicates the same thing, I being the row number that we're on and j being the column number that we're on. You can think of it as latitude and longitude. Like, how do you determine your position on a map? How far do you have to go left and right? How far do you have to go up and down on that map? Or as, like, not exactly the same, but kind of like your x and y axis, except it's flipped. So again, we use I and j to indicate where we are within the matrix. What element are we at? So A23, which I'll circle, that's the second row in the third column. So I is equal to 2 and j is equal to 3. We use the letters m and n to indicate the size of the matrix. How many rows are there in total and how many columns are there in total? So this matrix that's shown here with m rows and n columns, the bottom right entry in that matrix would be A sub mn. And I can't remember if I said this, but we describe the dimension of the matrix using m and n. We have two special shapes of matrices. We have what's called a row matrix, or also called a row vector. It is a 1 by n matrix. So one row and then some number of elements inside that row. It's called a row matrix because it is literally the shape of one row of a larger matrix. And then a column matrix, or column vector, is just the part that goes up and down with everything fitting in one column. That would be an m by 1 matrix. And we'll work with that notation. We'll work with those conventions throughout this section and the next. Before we march ahead with defining matrix operations, I want to solidify this idea of I and J being the index for elements inside a matrix. So let's look at this gigantic matrix. It is 6 by 6. So M is equal to 6, N is equal to 6. Has 36 elements inside it, and this question on the left-hand side is asking us to indicate what a selection of those elements are, just to get some practice with using this index notation. So the matrix entry or matrix element A35, that means we're going to row 3, column 5. So row 3, 1, 2, 3. So we're in here. We're in this row. And then column 5. So 1, 2, 3, 4, 5. We're inside that column. So our answer is 24. All right. Now the next one, A53. That's row 5, column 3. So I go to the 5th row, which is this one, and I go to the 3rd column, which is here. So 6 for that one. Okay, and now we'll go to the next one, A61. So we're going to row number 6, which is the last row, and then column 1, the first column, so our number is 4. And then the second last rather, we have A13, so first row, so this row, and then 3rd column, 0. And the last question is asking with the alternative notation, the 4-3 element of matrix A, so that's telling us to go to row 4, column 3. So this is the 4th row, and this is the 3rd column, so the answer is 3. That's how you traverse a matrix, or how you find the matrix entry or matrix element based on what the I and J label are. This slide just goes over some sample matrices describing their size and describing what some of the entries in each of the matrices would be. So the first matrix in A has 2 rows and 3 columns, so we would call it a 2 by 3 matrix. If we were asked for the 1-2 entry, that would be first row, second column. So 1-2 entry is 2, and the 2-1 entry is 4. So second row, first column. The next one over B is a matrix that has 5 rows. So 1, 2, 3, 4, 5 rows, and 2 columns. So it's a 5 by 2 matrix. We can index the 1, 2, and 2, 1 entries as indicated there. The next one is a column vector or column matrix. It consists of 1 column and 3 rows. So again, you have to be, mindful. Where what are the rows? 1, 2, 3. Those are the rows. So there are 3 rows. It looks weird. Each row only has 1 thing in it, but there are 3 of those rows. So it is a 3 by 1 matrix. The 1-2 entry doesn't exist because that would be first row, second column, and there is no second column. So no second column. But the 2-1 entry does exist. It's equal to 1 in this example. Okay, and the fourth vector here, vector D, is a row vector. It has 1 row And there's 4 columns, and yes, there's 4 columns. Each column is very boring. It has one number in it. Here's the first column, second column, third column, fourth column. It has a 1-2 entry, first row, second column, that's 0, but it does not have a 2-1 entry because there is no second row. And then a peculiarity of this matrix vocabulary, this matrix language, and this matrix construction is that we do have something that is not a number that consists of one element, and that is a 1-by-1 matrix. 1 row, 1 column. There's no 1-2 entry, since there's no second column, and there's no 2-1 entry since there's no second row. A peculiarity of the definition of column vector and row vector is that the matrix in E with a single element is neither a column nor a row vector, because the definition requires that the number of rows be larger than 1 or the number of columns be larger than 1 in order to qualify as a row or column vector. That's just pickiness, I think. Now, we have a lot of new vocabulary inside this section. Hopefully it's fairly clear what the vocabulary is and the connection between the word itself and the corresponding properties of the matrix that the word describes. In the first example, the 0 matrix is just a matrix that's filled with zeros. It can have any number of rows or any number of columns. What's pictured here is a 4-by-4 matrix filled with zeros, but you don't have to have the number of rows equal to the number of columns. You can have a 5-by-7 zero matrix. So what that means is if you're told that something is a 0 matrix, it's very ambiguous. It doesn't define the size. All that it says is that all the elements are 0 inside that matrix. Another piece of vocabulary we have is that there's something called a square matrix, or actually a whole bunch of them. And it's any matrix where the number of rows equals the number of columns, independent of what the elements are, independent of what numbers are in there. So they don't have to be the same, they don't have to be different, they don't have to be 0, they can be anything. All that matters is number of columns equals number of rows. Within this square matrix, if we look at the elements that are highlighted in yellow in this picture, we would say that those elements are along the main diagonal of the matrix. And every square matrix has a main diagonal. Square matrices are very important, and the diagonal of a matrix is often very important. And that's why there is special vocabulary and special categories for these things. The next type or species, if you want, of matrix is a matrix that is diagonal. And what that means is that it has to be a square matrix, so number of rows equals number of columns, and it specifies something about the entries within the matrix or elements within the matrix. And that's that everywhere except the main diagonal, those entries must be 0. Now, that there are allowed to be 0 entries along the diagonal as well. That falls within the definition of a diagonal matrix. But if it's a diagonal matrix, then anything that's not on, I'll highlight this one as well, anything that's not on this line, anything not there must be 0 or does not qualify. Now you look at the definition over on the left-hand side, it looks kind of weird. It says that a diagonal matrix is defined as follows. It has to be square and aij must be 0 if I does not equal j. So just hold on, don't panic. This is what it means. aij is the index indicating the value or the element value at row I, column j. And this is saying that if the column number does not equal the row number, and think about what that means. So if the column number is equal to row number, so let's say column number is 2, row number is 2, well, where does that go? So here's row, oh, don't want the purple highlighter. Very dangerous. Here's column 2, here's row 2. So that's the 2-2 entry. This one's below that is the 3-3 entry, and the top left is the 1-1 entry. Notice in all of those entries, the row number and the column number are the same. And that's always true for a number along the main diagonal. The column number has to equal the row number. And that's what this definition is saying. That if the row number does not equal the column number, so I does not equal j, then that means that this is not an element along the main diagonal. And that if this is a diagonal matrix, then that element must be 0. The element that's not on the main diagonal, the element where I does not equal j must be 0. And then the last, not the last of all, but last on this slide, piece of vocabulary or the last species or subspecies of matrix is something called an identity matrix. And an identity matrix, first of all, has to be square. Second of all, has to be diagonal. And third, the numbers along the diagonal must all be 1. So it's a matrix that's filled with zeros and ones, and the ones have a particular pattern. They're going from the top left to the bottom right only on that main diagonal. If you turn one of these into a 0, like at the bottom right, it's no longer an identity matrix. It has to be ones all the way down. The notation is that aij is equal to 0 for I not equal to j, so that's the same notation for a diagonal matrix, and that aij is equal to 1 if I equals j. So if the row number is equal to the column number, which means we're on the main diagonal, then the number that's there, so the value of that element must be 1. So that's how it's specified using the ij notation. Identity matrices are extremely important. We give them their own name. We call them the capital letter I. So that's indicated down here. And we specify their size using a subscript. And we only need one letter because they're square. So I sub n, where n is the number of rows and the number of columns, again, because it's a square matrix. If it says, for example, I sub 5, then that means it's a 5 by 5 identity matrix with ones along the main diagonal and zeros everywhere else. What we did when we first learned about numbers, just counting, I think we start learning to count to 5, and then we go to 10, and we start counting backwards, we count by 2s. We do very simple things with numbers when we're young. And then once we're better with understanding what numbers are, how to count, the relationship between, let's say, odds and evens, once we get good with that type of a thing, we move on to operations with numbers, like adding numbers and dividing and subtracting and multiplying and all those types of things. And you had a similar experience when you learned about vectors. You learned a little bit about what vectors were, and then about 10 minutes later, so much quicker than when you learned about numbers, you learned how to add vectors together. And then later, a week after, you learned how to multiply them together. But we're going to do something similar with matrices. We're going to learn how to add them together, how to subtract them, and how to multiply them. Division is going to take a bit longer. We'll still do that in the same, in sequence, but it's a much more complicated operation. Before doing that, I think it's good to take a pause and move to a second video.